The law of conservation of energy states that energy can neither be created nor destroyed. Rather, energy is simply converted from one form to another. As an example of this is the water feature at the entrance of Petco Park. As the water falls down the water feature, the stored gravitational potential energy converts to kinetic energy. When the water is at the top of the waterfall, before any movement, all the energy is stored as potential energy. Once the water begins to fall down, the gravitational potential energy is then converted to kinetic energy. The further the water falls, the more kinetic energy it gains. Thus, the water is moving faster when it hits the bottom of the waterfall than when it first went over the edge. When the water is recycled through the water feature, work is done on the system via a motor pump in order to get the water back to the top of the waterfall. The work done on the system is what's stored as gravitational potential energy at the top of the waterfall.
The force that a person in an elevator feels is the normal force, or the force of the elevator acting against another force. In this example, that force is the force of gravity. As the elevator travels up, its acceleration is in the positive direction, which is why the acceleration of the elevator is added to the acceleration due to gravity. This creates the feeling of being heavier as an elevator moves up from one floor to the next. As the elevator travels downward, the acceleration of the elevator is in the negative direction. However, the acceleration due to gravity is still a positive number. When combining the two terms mg and ma in order to find the normal force, the acceleration from the elevator must be subtracted from the acceleration due to gravity. Because of this difference, you experience the feeling of feeling lighter as an elevator moves down a floor.
After the ball is immediately thrown, velocity of the ball is in the positive direction, upwards. However, acceleration is in the opposite direction, down towards the earth. This is because the acceleration downward is the acceleration of the ball being pulled down back to earth due to gravity. Since the velocity of the ball and the acceleration of the ball are in opposite directions, the ball slows down. At the apex, or top of the parabola, the velocity of the ball is equal to 0. But since the acceleration of the ball is constant and still accelerating down to earth, the ball begins to fall back towards the earth. As the ball falls towards the earth, velocity is in the negative direction, or back towards the earth. Since velocity and acceleration are now in the same direction, the ball begins to speed up as it approaches the catcher. The acceleration for the entire system is a constant negative 9.8 meters per second squared.
There are multiple torques that go into the motion of pitching a ball. However, two of the main torques that go into performing this motion are the torque created by rotating the leg inside of the hips and the torque created from rotating the arm inside of the shoulder socket. Keep in mind that this is an extremely simplified model of what actually happens when a ball is thrown. The torque around hips rotates with a radius where r equals the length of the torso plus the length of the arm. The torque inside the shoulder rotates with a radius where r equals the length of the arm. By adding these torques, we can find the total torque created by the pitcher. Before the pitch, the ball had a chemical potential energy, a form of potential energy related to the structural arrangement of atoms or molecules. During the pitch, the pitcher transfers energy from his body to the ball through the torques. After the pitch, the ball leaves the pitcher's hand. The kinetic potential energy is converted to kinetic energy. Since the torque from the pitcher is also included, there is also rotational kinetic energy. This conversion is driven by the summation of the torques from the pitcher rotating his body in order to put enough force into throwing the ball. The energy from the pitcher winding up is then transferred into the ball, giving it its change in energy and ultimately enough velocity to reach the catcher. Since the ball rotates as it travels, we know that the torques also gave the ball rotational kinetic energy. The amount of rotational kinetic energy depends on the total sum of the torques, and more importantly, the torque created by rotating the wrist. This rotation accounts for many different types of pitches that can be thrown.
Work is dependent on the angle between the force on an object and the distance an object moves. However, forces that move at an angle perpendicular to the distance traveled do not affect the amount of energy transferred during that motion. Therefore, as the cotton candy man picks up his tray to begin his route, or lifts the tray after he has stopped to sell some of his product, he is doing work, because the angle of his motion is not perpendicular to the distance the object travels. However, when he is walking around the stadium carrying the cotton candy tray in the air so that people can see his product, he is not doing work because the force that is used to hold the tray up is perpendicular to the distance traveled. The reason he gets tired of holding the tray in the air is due to the stress on his arm muscles, not because he is actually doing work.
Different types of bats create different final velocities of the bats. For example, metal versus wooden. Here we use the average speed of a wooden bat, specifically a Louisville Slugger that weighs 26 ounces. Since only wooden bats are allowed in MLB and Louisville Sluggers are the most common brand used. The average weight of a baseball used in the majors is 5.125 ounces. The average speed of a bat entering a hit is 20 miles per hour, and the average speed of a baseball before contact is 90 miles per hour. The average speed of a bat after contact with a pitch is 60 miles per hour. If we plug all of these values, we can find the average speed of a baseball after it leaves the bat. When looking at a bunted ball, you should use the formula for conservation of energy. This shows that the ball leaves the bat with exactly the same amount of energy as it has before it hits the bat. Since we used the conservation of energy equation, we know that the ball can now travel off in any direction. This is why bunts can fall straight down or pop straight up. In order for the ball to stay in the infield, the batter has to pull the bat backward to try to control the distance and the direction that the ball travels.
Okay.
Sound waves are longitudinal waves that can travel through any material medium. The speed of the sound wave depends on the medium it travels through. For example, sound waves traveling through seawater travel approximately 5 times faster than sound waves through air. At a Padres game, there are plenty of sources for sound, one of the most obvious being the loudspeakers. Depending on where a person is seated or standing in reference to the source of the sound, in this case the speakers, will determine the frequency at which the observer will hear the sound. This is known as the Doppler effect. Motion of the source or observer toward the other results in the observer hearing a frequency that is higher than the true frequency emitted by the source, whereas motion of the source or observer away from the other results in the observer hearing a frequency that is lower than the true frequency of the source. This occurs because as the observer moves towards the sound source, the period of the sound wave becomes shorter. Each sound wave reaches the observer faster as the observer walks into each successive wave compared to if the observer stood still. Thus, the frequency of the sound is also higher. The opposite effect holds true for an observer walking away from the sound source and in the direction of the emitted waves. Each wave takes longer to reach the observer, producing a longer period and lower frequency than if they were stationary. These effects occur due to the relative speed of the observer to that of the sound wave. When the observer is traveling toward the sound source, the relative speed of the observer is higher than that of the wave of the speed, and vice versa for when the observer moves away from the sound source. The observer's relative speed is lower than the wave speed.
Waves are a transfer of energy, not matter. There are different types of waves, such as mechanical, electromagnetic, or sound waves. All these varieties of waves can be found at Petco Park. You can look out over San Diego Bay and see ripples in the water behind sailboats, an example of mechanical waves. You can see electromagnetic waves from the giant stadium lights, and you can hear sound waves from the speakers. Waves can also be categorized as longitudinal or transverse. In longitudinal waves, the elements disturbed move in a direction parallel to the propagation of energy. Transverse waves move perpendicular to the propagation of energy. If we're talking about waves at a baseball game, this example of transverse waves is definitely the most fun.